Example 8 is a little bit more complicated. We're actually going to be dealing with a couple of unknowns. So let's analyze this. We're going to find k so that this function, f of x is equal to x squared plus kx, will be tangent to this line. So for this to be tangent, we want the line to basically glance off of the function, right? And this is a quadratic, so I have a visual for that. And then we're also going to find what the x value is. So we're looking for both the k and the x. Well, what does tangent really mean? Tangent is twofold. When we're talking about tangency, the first thing is that the point has to be the same. So if I'm talking about a line being tangent to a function, that means they share one singular point with one another. So the point has to be the same, and also the slope has to be the same. At that split second in time, at that point, the slope of the function is also going to be equal to the slope of the line. So that's really what tangency means. So let's take a look at how we're going to set this up. If we want the point to be the same, that means we want x squared plus kx to be equal to the 2x minus 9. We want these two equations to share a point. So this line is going to touch this function at one particular moment in time. We also want the derivative, which represents the slope, right? We want the slope of this guy to be equal to the slope of this guy. So we know that f prime of x has to be equal to 2. The 2 is going to be the slope. This is a line. So the derivative of this is definitely 2. So I do know what f prime of x is. F prime of x is going to be 2x plus k, because k is treated as a constant. So the derivative of kx would just be k. So let's start here. Let's go back over to this other side and see what we have. If I'm going to try to solve this, is basically a system is what I've got. So if I'm going to try to solve this, it would probably be best for me to work with substitution. So I've got x squared, plus if I could plug in something for k, right? If I could put something in for k, then I would just have a bunch of x's that I could solve for. Well, lucky me, I can solve for k. So I'm going to solve for k here, 2 minus 2x, and then I'm going to take that and I'm going to plug it in. So I'm going to put 2 minus 2x in that spot, and now this becomes an algebra problem. So I've got x squared plus 2x. There's a little distribution. Hopefully y'all can see that. So we're distributing here. And then I've got minus 2x squared, right, equals 2x minus 9. So let's combine our like terms. Looks like I end up with negative x squared plus 2x equals 2x minus 9. There's a few different ways that we can go solve for this, but if we notice, if I'm trying to get everything on one side, once I subtract, my x goes away. So I'm left with negative x squared is equal to negative 9. Now I could move the 9 over and factor, or I could divide both by a negative 1. And now my result becomes the plus or minus 3. So I know where the x value will be with the point of tangency, right? So those are going to be my x values. The question is, what is the k when x is 3 and negative 3? So that's kind of the next step in the process. So we already have an equation for k. Again, this is just a system. So probably I could do k of, right, because this is a function of x. So I could do k of 3. So if I would plug in a 3 everywhere I see an x, that's going to end up giving me a negative 4, and I could do k of negative 3. Just be careful with your signs, right? So when you do minus a negative, you do end up with a positive, and you end up with 8. So there's a few different ways to write this out. This is a little ambiguous, but I would probably say at k equals negative 4, point of tangency, and you can abbreviate, just make sure it's clear, is x equals 3, and then at k equals 8, point of tangency is x equals negative 3. So that solves for both of the unknowns, both k and x.